I hope I be able to record this video without the storage closing it. But in case I closed suddenly, it's because of the storage, but I'll make sure to fix it until the next video comes. This is a playlist to help you revise for the International AQA A-Level Physics, AS Physics, as soon as possible. I'm trying to finish the video as soon as possible. We've done the first two parts, and in this video we will supposed to do more than one part, but at least we'll be doing the conservation rules, inshallah, if the storage was good. Okay, so the conservation rules are basically that all particles obey certain conservation rules when they interact. The conservation of energy, for example, as in all changes in science, not just particles interaction and decays, but the amount of energy remains fixed in a system as well. It was said in the O level that that energy is never created or destroyed, but rather transferred. This also applies to the rest of energy of a particle. Energy may be seen to have been lost, however, this lost energy may have been converted into mass. Following this rule, E is equal to mc squared. No exceptions have been found for this law. But for the conservation of charge in any interaction or decay, the total of the charge of the particle before the interaction or decay is the same as the total of the charge of the particle afterwards. Same for the energy can never be created nor destroyed, but rather can be transported. In is equal to out. No exception have been found also to this law. The conservation of lepton number in any change, the total lepton number for each lepton branch before the change is equal to the total lepton number for that branch after that change. All leptons have lepton number positive 1. All antileptons have lepton number negative 1. And we've talked about leptons in more details. If you'd like to screenshot or go watch the video, it's okay. But if you'd like to screenshot, here it is. Okay? Okay. I think that was the only part for that. I'm not sure. Anyways, yeah, it was the only point. Yeah, it was the only point. Okay, and if we talk about it in much like general points up, but this is the detailed part. Okay. Conservation of the branch of lepton also applies that lepton electron muon and TO number is always conserved. This can be useful to find out which type of neutrinos are emitted during certain decays. Conservation of strangeness. In any strong interaction, strangeness is always conserved. The total of all the strangeness of the particles before the change is equal to the total strangeness of the particle after the change. It's not conserved, however, when the weak interaction is involved. Conservation of baryon number. So here's an exception for the strangeness. It's not conserved, however, when the weak interaction is involved. Conservation of baryon number is the last one. In any charge, the baryon number before the change is equal to the lepton number after the change. All baryons have baryon number positive 1, all antibaryons have baryon number negative 1, and all mesons or leptons have baryon number O. This can be also thought of through quark change, as each quark has baryon number positive 1, 3. We are done with the part we were supposed to do, but I'll keep on going until it closes. Okay, I'll also write in the description, inshallah, what lessons were covered. Quantum phenomena. Electromagnetic waves. The electric and magnetic fields are perpendicular both to each other and the direction of propagation of the particle. There is no need for a medium for an electromagnetic wave to travel through. We have wavelength, which is defined as the distance between two adjacent points in phase in a wave period. The period of a wave is defined as the time taken for the one whole wave to pass a point through space, p equal 1 over f, and the wave speed of the wave is equal to distance traveled by wave in one cycle divided by the time taken. So c is equal to wavelength over 1 over f, which is therefore c is equal to f wavelength. The photoelectric effect. The photoelectric effect is a type of quantum phenomena that shows the light can behave as a particle as well as a wave. The photoelectric effect can only be explained with regards to light acting as a particles or quanta of energy. Experiments showed that when light was shown on a metal, electrons could be emitted from the surface of metal. However, emission of these electrons were dependent on several factors. The photoelectric emission of electrons from a metal surface does not take place if the frequency of the incident electromagnetic radiation is below a certain value, known as the threshold frequency. Threshold frequency is dependent on the type of metal used. Note as C is equal to F wavelength. The wavelength of the incident light has to be below a maximum value. The number of electrons emitted per second is proportional to the intensity of the electromagnetic radiation as long as the frequency of that electromagnetic radiation is above the threshold frequency as discussed before. Photoelectric emission occurs instantaneously provided the frequency of the incident electromagnetic radiation is above the threshold frequency. Explanation of the photoelectric effect. The photon model of light. Electromagnetic radiation consists of packets, the quanta of energy, known as photons. The energy of each photon can be found using the following formula. E is equal to hf, where h is the Planck's constant and has this constant value 6.63 times 10 to the power of negative 34, and f is the frequency for the electromagnetic radiation. When light is incident on metal surface, an electron at the surface absorbs a single photon from the incident light and therefore gains energy equal to hf as calculated using the formula above. As an electron can leave the metal surface if the energy gained from the single photon exceeds the work function of the metal. This is the minimum energy needed for an electron to escape from the metal surface. The work function has this symbol. Hence, it can be seen that the maximum kinetic energy of an emitted electron follows. Maximum energy is equal to hf minus the work function. Emission can take place at the surface at zero potential as long as the electron emitted has some kinetic energy. The work function of a metal is related to the threshold frequency. Frequency minimum is equal to work function over Planck's constant. An emitted electron may have energy less than the maximum kinetic energy of protected by the formula. It happens when the electron is not removed from the surface but from deep within the metal. In order for the electron to escape from the metal, it has to work its way up to the surface doing work and losing energy in the process. As a result, the energy it has on leaving the surface of the metal will be less than the energy it absorbed from the photon minus the work function. Remember that one photon hits one electron, giving it all the energy it had. This is the end of this video. In the next video, we will be completing the photoelectric presented on graph and the collision. Oh, actually, let's do this. The photoelectric effect represented on graph. If the maximum kinetic energies of the emitted electrons at different frequencies are known as the work function and threshold frequency of that metal can be calculated by means of a graphical method, as we see over here. On the y-axis, we have the energy, and the x-axis frequency. The work function starts from down, threshold frequency. Then we have the gradient, which is the slope, which is the Planck's constant. Vertical axis represents the maximum kinetic energy of the electron that has been emitted. Positive energy represents the kinetic energy of the electron emitted. Negative energy represents how much energy of the electron that absorbs a photon is lacking from being able to escape the metal. The horizontal axis represents the frequency of the light striking the metal, and we can use the graph to find several things, such as the x-intercept of the graph represents the threshold frequency of the metal. An emitted electron will have zero kinetic energy if it has just absorbed the photon of the threshold frequency. Second, that the y-intercept represents the negative value of the work function of that material, and that photons with zero frequency have no energy. The receiving electrons would have gained no energy and therefore would need a certain amount of energy to be emitted. This is the work function. Lastly, looking at the graph, the gradient represents the change in energy divided by the change in frequency. That is how much the maximum kinetic energy would increase if the frequency increased by 1 Hertz. Using the equation, E is equal to hf, rearranging to find h is equal to ef, as E over f represents the gradient of the graph. It can be seen that the gradient of the graph represents h, which is the Planck's constant. So this is actually the end of the video, and in the next video we'll be doing collision of electrons with atoms. If you'd like to screenshot the things to be ready for the next video, it's okay. Here you go. Also, you can see PMT to find it, photon emission, fluorescence, and the fluorescence tube. And that's it for the next video, I guess so.